Hi, I'm Teacher Thomas. Welcome to A-Level Maths. This is the specimen paper for 9231 Further Pure Mathematics 1 for the 2020 exam series, question 6. The position vectors of the points A, B, C, and D, which are given. M is an integer. It is given that the shortest distance between the line through A and B and the line through C and D is 3. Requirement A, show that the only possible value of M is 2. We'll begin with general equations for two lines. R1 equals A1 plus B1t, and R2 equals A2 plus B2t. The shortest distance between these two lines is the absolute value of the ratio of the difference between the position vectors A2 minus A1. We want the dot product of that value and the vector product of the direction vectors B1 and B2. In the denominator, the magnitude of the vector product of the direction vectors B1 and B2. Per the requirements, we want the line through A and B and the line through C and D. For the line through A and B, our line equation, I'll call this R1, we'll start at A, 2i plus 4j minus 3k plus t. Here we're going to take the difference of b minus a for I, j, and k. So we'll multiply t times first negative 2 coming from the b minus 2 applied to I plus 5 minus 4 j plus negative 4 minus negative 3 k. I can simplify the direction component as t times negative 4i plus j minus k. Relating to points C and D, we'll call this equation R2. Starting at C, I plus 4j plus k, and our direction vector plus t times first the I values, d minus c, 1 minus 1, I, plus 5 minus 4, j, and the k values, m minus 1, k. And again, I'll simplify the direction component to plus t times, there will be no I value, j plus quantity m minus 1, k. Now to find the vector product of B1 and B2, I'm going to set up the vector determinant. I will have I, j, and k. These values are coming from the direction vector for R1 and the direction vector for R2. I, j, and k for the direction vector from R1, negative 4. 1, negative 1, and the same for R2. I is not there, that's a 0 value, 1, and quantity m minus 1. I'll label these for reference as B1 and B2. Now I'm going to use minor determinants to find I, j, and k. For I, I'll use the minor determinant for j and k. So I'll multiply the B1j times the B2k, that's 1 times m minus 1. I will subtract the product of B2j and B1k, 1 times negative 1. This will be the I value. Minus, notice for the j I have a negative sign, so minus, for j we'll work with the minor determinant of I and k. I'll take the B1i, negative 4, times the B2k, which is m minus 1. I'll subtract the B2i times be 1k. 0 times negative 1. And adding for k, I'll use the minor determinant of I and j. So the b1 value for I times the b2 value for j, negative 4 times 1, minus the b2 value for I times the b1 value for j, 0 times 1. I need to bring in my j in the second line and my k in the third line. When I simplify, the I term is mi, plus the j term is 4m minus 4, j. The k term is negative 4 minus 4k. Now our distance calculation. We're given the distance is 3. 3 equals, I'm going to mark over on the far left to be clear, this is a2 minus a1, and I'm looking for an I value, a j value, and a k value. Looking at R1 and R2, we're using the position vector component, the first component of those line equations, and subtracting a2 minus a1. R2, the I coefficient is 1, minus the R1 coefficient of 2 is negative 1i, plus the j values, 4 minus 4, 0j, plus the k values. R2 has a k coefficient of 1, R1 has a k coefficient of negative 3, 1 minus negative 3 is 4k. We want the dot product of this expression and the vector product we just calculated, mi, plus quantity 4m minus 4j minus 4k. In the denominator, we want the magnitude of the vector product which we calculated. That's going to be the square root of the sum of each squared coefficient. The coefficient, and we're looking at the bottom of the middle column, the vector product we calculated. The coefficient of I is m, so I have m squared plus the coefficient of j is quantity 4m minus 4, that squared, plus the coefficient of k minus 4, also squared. And I want the absolute value. 3 is the result of an absolute value calculation. Simplifying, we have 3 equals the absolute value in the numerator. The dot product is the sum of the products of the coefficients of I, j, and k. The coefficients of I are negative 1 and m. We multiply to negative m. The coefficients of j include a 0, so those will multiply to 0. And the coefficients of k, 4 and negative 4, product is negative 16. In the denominator, we're going to expand. We'll have the square root of m squared plus 16m squared minus 32m plus 16, which is plus 32. Now I'm going to momentarily disregard absolute value, and I'm going to cross multiply to end up with the right side denominator as the left side numerator. So that is going to be the square root of m squared plus 16m squared is 17m squared minus 32m plus 32 equals, and on the right I have negative m minus 16 over 3. The result of dropping the absolute value notation is now that if that negative m minus 16 produces a negative value, my equation won't work. However, I'm going to square both sides to remove the radical from the left. 17m squared minus 32m plus 32 will be negative m minus 16 squared over 3 squared, which is 9. So now negative m minus 16, whether that had been positive or negative, that expression is going to be squared, producing a positive value. From here, you can work through further algebraic manipulation. You'll end up solving a quadratic. The values for m, when you solve the quadratic, are 2 and 2 over 19. In the requirements, we're told m is an integer, so 2 over 19 isn't a possibility, and our final answer, m equals 2. This completes the requirements for question 6, part A.